So today we have Dr. Jeff Williams, who obtained his Bachelor of Science and PhD from the Department of Mathematical Physics at the University of Birmingham in England. His thesis concerned the topological description of intrinsic spin on elementary particles. He then did a postdoctoral fellowship at the Department of Physics at the University of Alberta, and then one at the University of Brussels in Belgium. He subsequently became a statistician at the Queen Elizabeth Hospital in Birmingham, England, and then moved back to Canada, where he took a position as an assistant professor at the University of Calgary, where he continued his work in topology, and but then in reference to general relativity. Later, he took a similar position at Mount Vincent University in Halifax. And then in 1986, he joined the Department of Mathematics and Computer Science at Brandon University, where current research focuses on null-surface formulation of general relativity. So I'll turn it over to Dr. Phil.
Yeah, thanks, Linda. My whole life sort of condensed down to a few minutes. I'm impressed. So yeah, welcome everybody. I should mention that the few results that you're going to hear that are new were done in collaboration with my colleague, Dr. Tina Harriott, who's a professor of mathematics at Mount St. Vincent University in Halifax. Here she is, and yes, she is a pilot, and that's her aeroplane. But just moving along, people say that maybe every seminar should start with a story. So here's a story for you. This is the village of Dolmieu. It's in eastern France, southeastern France, not far from the Swiss border. In fact, on a clear day, if there were no clouds, you'd be able to see the Swiss Alps from the main street here. In the year 1869, the wife of the village blacksmith, a certain Madame Cartin, gave birth to a baby boy. Parents took the baby along to the parish church, and they christened him Ivan, or Eli, pronouncing it the French way, perhaps. And so young Eli Cartin, he grew older, eventually went to the village school, and life would have progressed. Had fate not intervened, life would have progressed in the usual way. He would graduate from the school in the village. He would become an apprentice blacksmith and study under his father, and then become a fully fledged blacksmith. But France at the time was a very centralized country, or still is in a way. Everything was run from Paris. And the French had a system of school inspectors who traveled around the schools. This predates railways to some extent, or probably on horseback then. And their role was to see that the schools had equal standards across the country. Another role of the school inspectors was to talent spot bright young students. And when the inspector went to the school at Dolmieu, he was very impressed with young Eli Cartin, very impressed with the lad's ability in mathematics. And so he recommended him for a scholarship to go and study in the Lycée Henri IV, the most famous high school in the whole of France, located in Paris, of course. And so the young boy went out to Paris. And he studied at the school in Paris. He did very well. And then he went on to the University of Paris, where he studied mathematics. Again, he flourished at the University of Paris and eventually became a professor there. Here he is, Eli Cartin. One of the most famous professors of mathematics of his day. He studied many things. He made many discoveries. He introduced aspects of differential geometry, in fact, largely considered to be the father of differential geometry. And one of his projects was to look at differential equations as a whole. Differential equations, probably many people know, are equations which are out of calculus, but dominate much of science, particularly physics, aspects of chemistry. And there are a myriad of them, and solving them is quite a skill. And Cartan's idea was there should be some sort of taxonomy, some sort of way of categorizing differential equations, putting them into groups so they could more easily be studied. And he worked at that quite a while, and eventually became discouraged because in the end, his classification scheme depended upon an equation which he wrote down. He did publish the equation, but he was so outrageous, such a ridiculous equation, that he couldn't imagine anybody being able to make any use of it, let alone solve it. And so he plenty of other things to do, and so he moved on to other aspects of mathematics. And let's just leave the story hanging there for a moment, because I'd like to introduce time. Time, something everybody's familiar with, everybody understands, until maybe you start to think about it and wonder how well you do understand it. It does have the odd feature of always going in one direction. Always increases. We seem not to be able to slip back, much as we might like to, but seem not to be able to slip back in time and sort of change our. And then there's space. Very different concept. There's certainly in the mind of Newton, space extension. Unlike time, it comes in three dimensions. Time, if you like, is just one thing, space, three different directions, forward, backwards, side to side, up and down, if you wish, measured by rulers. If time is measured by clocks, space is measured by rulers. Chance, I happened to photograph a ruler that came out of Pittsburgh. Pittsburgh, you'll hear later on in the course, plays a particularly important role in the subject of this talk. Let's just backtrack. Right. Although Newton, certainly Galileo, considered time and space as two very different things, around about 100 years ago, slightly longer, people were coming around to the idea that maybe they weren't so different. Maybe space and time, there was some connection, some link. And it wasn't until 1905 that Albert Einstein cemented the link. Several other people thought of this idea, thought that space and time weren't totally separate, thought that the concept of space-time, if you like, that combined two ideas taken together would be worth considering. People like Lorentz in Holland, Poincaré in France, in Switzerland, Minkowski. He was Einstein's professor at Zurich Polytechnic, the guy who thought Einstein was a lazy dog. He was not impressed by Einstein. But anyway, here's a lazy dog. And in 1905, he came up with the unification scheme, special relativity. Again, though, if we ask this question, when did somebody first come up with the idea of linking space and time in this way? We shouldn't always give the credit to the scientists. It is novel The Time Machine, H.G. Wells. I'm not sure if there are any fans of H.G. Wells here. Famous British science fiction writer of the day, 1895 was when his Time Machine was published. And as he puts it there, I'll read it out in case people are too far away to read. There is no difference between time and any of the three dimensions of space. So imagine somebody saying that in the late 1800s. There's no difference between time and any of the three dimensions of space. And so certainly, ever since Einstein, one has tried to combine time with space very successfully. The problem that Einstein, though, was presented with after 1905, once he'd married space and time to everybody's satisfaction, was to bring in gravitation. That was the one thing that his special relativity did not include. He wanted a more general theory. He wanted space-time, he thought he was on the right track, but he wanted to include gravity. There's clearly something special about gravity, something that made it different from the other forces, different from, say, electricity or magnetism, that kind And 1915, it took him about 10 years to put together his theory of general relativity. Mathematically, it's quite challenging, partly because back in those times, physicists tended not to study differential geometry. Einstein at first didn't realize what area of mathematics he needed. He had good physical intuition, but what math to use? And so he contacted his old friend, Marcel Grossmann, again from the Zurich Polytechnic, kind of explained the situation to him. And Marcel Grossmann said, oh, yeah, Riemannian geometry, that's what you need, the differential geometry of Riemann. And so Einstein learned Riemannian geometry, created general relativity, and the theory was amazingly successful. It seems to have passed almost any of the challenges that have been put before it. There's the issue of dark energy and the issue of dark matter. There are some outlying troublesome features, but many things are explained by general relativity, theory of the universe, so on. So here's the picture that people usually look at. It's a bit deceptive. This curvy mattress thing on which the Earth is bouncing up and down, it's meant to represent space-time. If it does represent space-time, then it only has 2 dimensions. So space-time really needs 4 dimensions, but we're kind of scaling the number of dimensions down so we can draw the picture and get a little bit of physical intuition. So this idea of a large, massive object, the Earth, the Sun, distorting the fabric of space-time, so that anything moving through space-time it's not a level ground to them. There are dips that cause deflections in the motion. So here, maybe we can't quite see the red trajectory there. There's meant to be a particle or asteroid or something coming in from the left, following that red trajectory. It's passing by the sun, it's getting curved around. And so this is the explanation of how gravitation works in terms of differential geometry. Objects are deflected, sometimes trapped, they go into orbit. Right, let's backtrack a bit more, in fact. If we're talking about space-time, let's just look at space, and let's drop down to a single dimension. So we're living in one-dimensional space. There's a line, and that's it. That's all there is. There's no outside of the line. The line is it. Let's suppose the line there's a sort of positive sense to the line, so that is the x off to the right. And you turn on a light. You have a lamp, put it at the left-hand end, and you switch it on. There it goes. So the light travels outwards from its source. That. Yes.
Not sure.
You
You can try advancing. Oh,
now it's caught up.
okay. Just keep pressing buttons. That's
Okay. So the light travels. The light travels out to the right. Not a bad picture, but not an ideal picture if you're wanting some concept of space-time. Because the light is traveling not just in space, it's traveling in time. As one moves along from the left of the arrow towards the head, time is passing.
Just keep tapping on the button.
Yes,
There we go.
got it.
Yeah.
Okay. So this would be a better picture. Time traditionally in space-time diagrams is plotted vertically. And so that arrow should have some vertical component. So as one advances from the light source, the light moves along, it goes off in space, moving to the right in space, but it also moves up in time. So time passes, space is passed by. So that's a better picture. That's the space-time picture. And these space-time diagrams always plotted vertically, always space plotted horizontally. There's only one dimension of space here. Yeah, question, why 45 degrees? Let's have another look at the picture. Why is this at 45 degrees? It depends upon units. What unit are you going to measure distance in? Inches, miles? What unit are you going to measure time in? Seconds, hours? Probably doesn't matter that much, but it's going to control the slope of your graph. Light travels around something like 300,000 miles a second. And so if you were to plot this graph with miles going horizontally and seconds going vertically, that line would be practically horizontal. It would be almost along the x-axis and very hard to read. So usually one picks units appropriately so that light always travels at 45 degrees in these space-time diagrams. It makes it easier to understand the diagram. So nothing special about that 45 degrees. Let's add another dimension. So we have the x coming out one way, a y. Let's add a second dimension of space, but time still vertically. And now my line that was tilted at 45 degrees, had we again turned on the light at the origin there, that light would spread along the cone. So it spreads along the cone, light cone, so-called. So the cone is that surface on space-time along which light is traveling. Now, this is assuming no gravity. Light is free to travel. It's not going to be deflected by the gravitational pull, which it would be if perhaps a star or galaxy were nearby. We're assuming that we're working in special relativity. We haven't introduced gravitation yet. Ted Newman, my hero, looks like he's out on a fishing trip. He's for many years was professor of physics at the University of Pittsburgh, and he's the person who was responsible for what's now called the null-surface formulation of general relativity. So this is another way to do general relativity. Einstein's general relativity, invented in 1915 by Einstein, amazingly successful. Maybe it's worthwhile having another equivalent theory. Maybe one can find out different things, understand different aspects of reality by looking at a second version of the theory. And he's the person who thought up the second version that myself and my colleague Tina have been working on for a little while. And the second version involved using light beams, light surfaces, and understanding how they were deflected. So instead of studying general relativity, one studies surfaces in space-time. One formulates all of the equations, all of the theory in terms of the surfaces. One surface you've seen already, it's the light cone surface. Next one. Yeah, the title here, View from the End of the Universe. What is this saying? What is this title saying? Well, you're at the end of the universe. What's your view going to be like? You look back on the universe. Does this make any sense? Is Starship Enterprise is traveling across space, and Captain Kirk calls down to Mr. Scott and says, "Stop engine, Scott, because we've reached the end of the universe. There's nowhere else to go." It's not that there's empty space beyond, but there is no space. It's the end of the universe. Does it make sense? Well, let's think of the following picture. As I sort of hinted at earlier, perhaps the scientists shouldn't have the sole domain of science. Perhaps artists and writers like H.G. Wells have something to say. Yeah, who's the artist here? Who did this?
Escher.
Yeah, very good, Escher. Yeah, here he is. This is self-portrait. Yeah, Escher did some wonderful artwork. If you're not familiar with him, you should maybe look him up. Myriad of pictures, many of them involving strange symmetries. He worked with the Canadian mathematician Coxeter, one of the geometers at the University of Toronto, for a number of years. Escher is Dutch, of course, lived in Amsterdam. This was his self-portrait. Again, a very sort of clever geometric thing in which he imagined himself looking into this globe and seeing his own reflection there. But let's stick with the picture. What is this picture telling us? Angels and demons. You can see the demons. I hope everybody can pick out the angels, right? The white angels in there. And you look at this picture and you say, okay, this is drawn or painted on a circular disc, maybe, or maybe it's a piece of pottery. Maybe this is a dinner plate with this fancy design. So it's a circular dinner plate with this fancy design. And look at the design. We have these angels and demons, and they're quite big. In the middle of the plate, they're quite large. But as you get closer to the end of the plate, they get smaller. As you move away from the middle, they get smaller. And as you move further away from the middle, they get really tiny and become more numerous. More and more and more of them as you get closer and closer to the edge of the plate. It's one way to think of it. But a person might say, no, in fact, all of the angels and demons, they're all the same size. All of them, they're all the same size. It's just that what's happened here is we've got an infinite plane of angels and demons stretching on forever in every direction. And they're all the same size, but then somebody has pulled them in from infinity. And the ones that are far out are getting pretty scrunched up. There's a lot of them around the rim, infinite number of them, if you like. But as you get near the middle, then the angels and demons become fewer in number and become bigger. So this is a nice design. And this is exactly how a number of physicists, particularly Roger Penrose, still alive, one of the famous physicists of our days, thought of things back in the 1960s. So the idea is quite old, that if you would like to treat the universe mathematically and more easily, rather than dealing with something that's infinite, let's play this pretend game. Let's perform a mathematical transformation that brings the universe in. That breaks the universe into a finite distance. So infinity is a finite distance away. It's just several centimeters from the middle of the plate, if you like. It's not far away. It's a nice way to do things. And this way of doing things, this sort of transformation is well known to mathematicians. It's called a conformal transformation that can bring in an infinite region and present it in a finite span of space. Conformal transformation, it's been much studied over the years. But viewed in this light, the end of the universe, if we're thinking, well, you can bring in the universe, the whole of it, into a finite distance, into this room, if you want. So the walls and the ceilings, these are the end of the universe. There's no more space, no more space-time beyond here. So this presents a sort of interesting thought. So you're standing here in this finite universe, in the sense it's been pulled in by this mathematical transformation, and you have a flashlight, and you shine the flashlight up to the ceiling. You're going to get a nice pool of light. You're going to get a nice circle of light. If you tilt it a little bit, well, let's try doing it. So here's that. And if people are too far away there, maybe we'll try it. Too much light, maybe. All right, thank you. Thanks, Tom. Yeah, so here we've got a nice circle. If I tilt it, it becomes more oval. But this is without any gravity, without any stars and galaxies. This is not how things would be set up if you were looking to create a theory of gravitation. If we suppose there are stars, galaxies around the room, what they're going to do is they're going to interfere with the light, interfere with the individual light rays. And so now the nice oval of light becomes crinkly at the edges. It's tracing out a curve, if you wish. And if you could understand that curve, you'd understand what had been happening to each individual light ray en route to that curve at the edge of space, and all the galaxies and stars that had deflected it. That curve tells you about the universe. And that's the idea of the null surface formulation. I have a kind of model here. So we're imagining that, okay. We're imagining that this is a boundary of the universe. So you might imagine, well, why is it sloping like this? Talk about that in a moment. And here's my curve. It's a fairly simple curve. It loops over itself, so that's a complication that can arise. And so the story here is, if you allow your light to start at a point, head off, reach the edge of the universe, and you follow that curve around, that curve will tell you about the whole of space-time and everything in it. Obviously, it's going to be a complicated curve. Obviously, the mathematical formula for that curve is going to be a little bit involved. So we don't have to have always angels and demons. Somebody's done this for your actual universe. So this is an actual picture from Space Telescope with various galaxies, and here's our sun right in the middle. And they've performed this mathematical transformation, and they've pulled in, and you can see all the more distant galaxies all scrunched around the edge of the dinner plate. So this is a real picture. Now, if you say, well, the edge of the dinner plate, it's not fully three-dimensional or 3+1 dimensional, the space-time. It doesn't have the full 3 dimensions of space and 1 dimension of time. So we want to scale up the dimensions. So let's scale up the dimension of space. And so instead of having just a circular boundary, which is what a dinner plate would have, a circular boundary, rather you need a spherical boundary. And so here's just half of the sphere. So here's a hemisphere. I need another hemisphere to slap at the bottom, and I create this kind of spherical egg thing, and the universe is within it, and the boundary is spherical. That's going up a dimension. Now, of course, we can't go up to full three dimensions of space and include time. So it's a bit hard to render this idea in 3+1 dimensions. But here it is, we scaled up by 1 dimension, we get this spherical dome. It would be better not to take the spherical dome but to take something like an inverted cone. That would be better. Once one thinks about it, the light rays, remember the light rays are traveling at 45 degrees. And so infinity, it turns out, can better be handled by having sloping sides like that. And this is how Penrose did it. His conformal infinity, his boundary of the universe, actually was like a sloping roof, circular. As I say, we're still 1 dimension down, so it's not really reality. And you can imagine underneath this, within it, where you perhaps can't see, you turn on a light and the light moves up and it strikes the underside of the dome and it forms a particular pattern. So this is more like it should be. It's more like an inverted cone. And as the light strikes the underneath, so it would form patterns. So it would form some sort of curve. There's a spot where I've been there.
Quite sure what's, yeah, it might be just going to sleep between the, just keep tapping. Or if you wanna go over the computer, you can just use the arrows, but
Oh, yeah. Oh, no, tapping's
just
done.
keep tapping away,
Yeah.
it'll figure it out.
Another obvious question should be, okay, so we have this new idea, this idea of bringing in infinity, studying what the curves are doing out there, and this is going to give us a theory of gravity, which it does, one that's equivalent to general relativity. But why? Why should we bother doing this? Why should you've got a perfectly good theory in general relativity, why should you bother getting another theory? Well, classical mechanics is a good example. Here's Isaac Newton, one of the main creators of classical mechanics, Newtonian mechanics, as it's called. And there's Newton's version, force equals mass times acceleration, amazingly successful, simple theory. Here's Lagrange. He had his own theory of mechanics, Lagrangian mechanics, a bit more complicated, but actually has lots of applications, somewhat more powerful than Newton's theory. And also in modern physics, the Lagrangian approach is very useful if you want to look at field theories of elementary particles. So it had different application from Newton's ways of doing things. Here's William Rowan Hamilton, a famous Irish mathematician. Hamiltonian mechanics, another version of classical mechanics. Again, a little bit more strange appearing than Newton's theory, but led the way into quantum mechanics because aspects of Hamilton's theory of classical mechanics sort of open a window onto quantum mechanics to a certain degree. The notation, the formulas are somewhat similar to quantum mechanics. So 3 different theories, with good reason to think about each one of them. We don't have to just look at classical mechanics. How about another physical theory, quantum mechanics? Here's Erwin Schrödinger, famous Austrian physicist, 1926, created quantum mechanics, wave mechanics as he called it, had a very definite wave point of view, solving differential equations for waves. Very useful if you're a chemist, you want to study the hydrogen atom. But there are other versions of quantum mechanics due to Heisenberg, for example. Very useful if you want to introduce quantum field theories because it focuses more on operators than it does on waves. And finally, whose picture's coming up next? Anyone want to make an offer? Another famous person in the quantum domain, but he was hiding somewhere. There he comes. Richard Feynman. Feynman, integral way of doing quantum mechanics. Again, if you want to study the wave function of the universe, for example, very different formalism, but again, another way of doing quantum mechanics. So certainly the inventors of the null-surface formulation and general relativity kind of inspired by this, thinking that maybe it's not a bad idea to have a different theory that's equivalent to one that already exists. So here we are, we're at the cone edge of the universe, the upper edge, be a cone the other way up the bottom. Here's my light. There it is, it's starting off at that point, the light is turned on. The light travels out at 45 degrees, as it should. One dimension's, well, we haven't drawn in all the lines, it's the entire cone that is going up, the entire light cone. It's cutting out a shape, that infinite boundary, as it were. And in this case, it's just a circle. If you move off center a little bit, this is a bit more realistic, and so the circle's slightly tilted, more of an oval kind of shape. So far, so good. And the idea is that in the null-surface formulation, in fact, this boundary is actually a null surface. It's 45 degrees, light can travel on it. So that's a surface on which light can travel. It's formed the boundary. And within we have this other surface going up, and it's creating this light cone cut, so-called, this curve at null infinity. Of course, reality is a bit more complicated. If you're sprinkling the universe with stars and galaxies, all of these curves are going to bend. And so the light cone, as it heads up, it's going to be a series of bent curves, and they're going to make the cut with some more complicated shape. So far, so good. But the null-surface formulation itself comes in a second version. So here's the second version of the null-surface formulation. So there you see the curve out at null infinity, as it's called, out at the boundary. It's drawn very simply. It should be more complicated than that, and should perhaps be at a tilt, but just drawing it as a simple circle. Supposing you're an observer, and you're standing there out at this infinite boundary, putting myself by the wall, by the boundary of space and time, and you look back into the universe. And so at that point P, person is looking back into the universe. They see the light rays coming up to their eye, and so they see all the incoming light. It's the view from the end of the universe. This is a time talk. And you can change your point of view. This person can wander around at this null infinity boundary, go to somewhere else, get a slightly different view of what's happening out there. As I say, the pictures are highly stylized and highly simplified because these straight lines should not be straight. They should be curving wildly and doing all sorts of contortions, but all sorts of different places you can look as you go around. And this is the second way to look at the null surface formulation. These surfaces, all of them, these inverted cones, so-called null surfaces, surfaces on which light travels, convey information about the universe. So if you know about, just pick one of these surfaces, if you know about these surfaces, these inverted cones, you know the exact shape, then you can tell all about the universe, about the different galaxies and stars, and distribution of matter, interstellar dust, and all of that kind of stuff, just from the surface. So this is again just to remind people that these things are curving a little bit more than some of the pictures suggest. So here's lots of surfaces. So if you've got a surface, as people know, if you've got a surface, you have an equation for the surface. And so the equation that controls the surfaces is the equivalent of the Einstein field equation. So every respectable theory in physics comes with its equations. So Newton's theory, Newton's equations, Maxwell's electromagnetism, we have Maxwell's equations, we have Einstein's equations and general relativity and so on. And sure enough, there's a differential equation, actually more than one, that control the null surface formulation. So the name of the game is, once you have the differential equation, and this was found by Ted Newman, whose picture I showed a minute or two ago, once you have the differential equation, solve it, and this will give you a particular configuration of matter. So perhaps one solution will correspond to a black hole, maybe one solution rotating galaxy, maybe one solution to the entire universe expanding or doing something, something interesting. Let's look at the differential equation. So this is the main differential equation to come out to the null surface formulation. So we look at this. If you're not terribly familiar with differential equations or calculus, maybe I'll just sort of explain a little bit of it. This is a fierce-looking differential equation. It involves lambda. That's the function you have to determine. You need to find lambda to solve this differential equation. Now, lambda is a function of various variables, as it says here on the right, function of u, omega, rho, and phi. So there are a number of variables here. This is what's called a partial differential equation. You can see some derivatives coming in here. So the term, looking at the equation, On the extreme right, where it says 6 del mu of lambda, that's a derivative with respect to the u variable. So the u, omega, and rho variables are kind of like using t, x, and y, if you like using the ordinary variables that describe space-time, t for time, x, y for position. But the variables in the null surface are a little bit mixed up. So we don't use exactly t, x, and y, we use these other variables, but that's fine. Doesn't matter which variables we use. So you've got that derivative coming in with a 6 in front of it. Move to the left, you have another derivative coming in, derivative with respect to the variable omega. Omega is to do with rotation, it's a sort of angular variable. But there's a 3 on that term, 3 del. What is the del? Well, it's telling you right at the bottom. So this equation is actually more complicated than it looks. Everywhere you see this operator del, it actually stands for a whole succession of operators, each one of them being a derivative and each being multiplied by a whole pile of stuff. Let's look at some of the other terms. The middle term, just standing right here, it involves differentiating with respect to rho, but then differentiating twice with respect to this operator. So differentiating 3 times. That's rather unusual in physical theories. This is what's called a third order differential equation. It's rather unusual. Physical theories tend to be first order, Maxwell's equations, second order, Schrodinger's equation, Einstein's equation, Newton's equation. Yes, second order is popular. Fourth order, not very popular, but elasticity equations are fourth order. Third order equations are almost never heard of. In fact, if anybody comes across one, please tell me. I'm trying to collect third order equations from other parts of physics. So extremely uncommon to be a third order equation. It's highly nonlinear, which means you're multiplying these derivatives together and multiplying in a rather complicated way. So this first term, 2 with the bracket, is quite a complicated so right. Yeah, my colleague Chen Quan, I remember when I first showed him this equation, he spotted the solution instantly. Always remember that, and said, oh yeah, lambda, the variable we're looking for, could just be a constant, could just be 1. Yeah, absolutely right, well spotted. And the trouble is, though, constant we can eliminate because such a thing would describe empty space. So we're not interested in describing empty space here. We want a theory of gravitation. So we want some matter around. And once you move away from the possibility of just having a constant, it becomes a bit tricky to solve this equation. This is the equation of Cartan. This is his famous equation that he came up with really at the tail end of his career. In 1932, Eli Cartan published this equation and kind of gave up on it. So it's certainly not true that myself and my colleague are smarter than Cartan. We're coming in from a different point of view. We're coming in from kind of the point of view of physics and a different take on it. And so once you start to think about it, it is possible to find a few solutions. In fact, most physicists would look at this and perhaps straight away come up with the idea, well, suppose my function only depends on one of the variables. This is commonly done with situations of spherical symmetry. You say, I've got a star, spherical symmetric situation, there is an X, Y, and a Z, but really all that matters is the distance away from the star, that radial distance. And rho here, the variable rho, which comes here, if you wish, comes in several places. You could think of this as the radial variable. And so if you say, well, suppose my function that I'm looking for only depends on rho. Well, then you have a way in. And yeah, there's Eli Cartan again. And the solution actually is deceptively simple. Here it is. So this function actually solves the equation. So rho is your variable. Think of it as r, radius, if you wish. You're doing some squaring. You've got some constants flying around, A, B, C. They're constants, make them anything you feel like. No surprise, there are three of them. The equation is third order. And so we would expect three arbitrary constants to be present. And sigma then is the 3/2 power of that expression that's quadratic in rho. And so that's quite an easy thing to understand, given the complexity of the equation. You could rewrite it if you don't like half powers. You could write it as the square root of something cubed. So at least two ways of writing that solution. What else can we say about this solution? Well, in actual fact, there are three equations to be solved. I didn't mention the other two equations of the null surface. And just like Maxwell's equations, so there's more than one equation. Same with null surface. Here's the second equation. It's for this variable called omega. Doesn't look too bad, and it's not too bad. Once one appreciates what lambda is, once one's found the first bit of the solution, this follows very quickly. And again, it's something that depends on rho in a nice quadratic way. It's a square root. And then the final equation, the third equation of the null surface formulation. Here it is. This is a linking with the Einstein's equations. Yeah, the first two equations of the null surface formulation, basically they give you space-time, give you the existence of space-time with the right kind of signature, the minus plus plus signature, which distinguishes time from space. This third equation is the tie-in with Einstein's equation. And again, people in physics, maybe chemistry, would recognize that T there, that capital T on the right, it's the energy momentum tensor. That kappa, positive constant, it's just Newton's constant of gravitation. It's capital G divided by 4 pi. And that equation isn't too hard to solve. And so one can come out, one can find the answer for T. So one has everything that one needs. This particular approach solves the equations completely. But of course, there are a myriad of other solutions. Of course, this is just one very simple solution. Here altogether are the three equations. One is what's called the main metricity condition. It's the most prominent equation of the surface formulation, hardest to solve. The second two, not too bad. And people who are kind of used to working maybe in relativity or maybe in fluid dynamics might ask the question, okay, so we've got this solution. This describes some sort of physical situation. But what is the physical situation? What is the material that is causing this gravitational field? Turns out to be a perfect fluid. Often used to model stars. So there's simply sort of fluid. There's no friction. Again, apologies. I know perhaps everybody doesn't immediately see these and recognize what this stuff means. The energy momentum tensor is sort of quoted at the top. These U's that are flying around at velocity. So you imagine you've got this fluid of stuff, of material, of matter. It's in this universe. It's flowing around. You can pick out the mass density. The mass density is lower left. Good news, it's positive. It better be positive. Mass density, you want to be positive, you don't want to be negative, but something that comes in there that's squared. So that's killing any negative signs. And that K at the bottom, I said Newton's constant, positive thing. To the right, pressure. One can calculate the pressure. Again, nice sort of thing. And one can, for those sort of in the know about equations of state, you probably sort of picked out the equation of state here, that the mu on the left, the mass density, and the pressure on the right, one is just 3 times the other. And so that's a nice tidy equation of state. So this is quite a nice solution. But that's it.
Is the T rule a function of rho in the third equation? Yes, here, yeah. Is the T rule a constant or function of rho?
Oh, it will be a function of rho. And in truth, that T is actually a matrix, which is why some matrix components are, it's the row component of the particular matrix, and it is a function of row. Yes, yes.
Alex?
So I'm curious, other than this being super neat, is there an application for this type of work? I mean, I'm not certain I followed all. Yeah.
Yeah,
but,
I mean, it's a very good question, and I wish there were more applications. Like there are people who feel that there's a connection. Quite a few papers been published using the null surface formulation for gravitational lensing, so that may well be an application in the end. There's certainly one publication out there at the moment, recent one, that links it in with global positioning satellites, because of the way the light works, basically. Yeah, there are relatively few applications. The difficulty is it is quite hard to work with. It's quite hard to find these solutions. So after we found this solution, which kind of surprised us in a way, we found 2 or 3 others, all of them very nice, for nice physical situations. What's called a scalar fluid, for example. And so there are solutions which correspond to physical settings, but yeah, there aren't that many applications yet. Maybe they'll come. Here.
I was just wondering, you mentioned, had been being a role model for you growing up, or not growing up, throughout your career. I was just curious if there was anyone who could maybe his work inspired you, or if there was anyone else in your field that really helped grasp some of these subjects,
Right.
or in your work.
Right. Yeah, good question. Yeah, several people, I suppose. My thesis supervisor for my PhD was very interested in learning topology. So I was lucky enough to have a supervisor who didn't know any topology at a time when I didn't know any topology, because it wasn't very common in physics at that time. And so we kind of learned together, and yeah, and so he was definitely somebody who's a great inspiration. But Ted Newman, yeah, once my colleague and I decided, oh, null surface formulation, it's a really neat thing. Let's go to Pittsburgh. Let's make a pilgrimage to Pittsburgh and see this guy. And he was very welcoming, just extremely welcoming and very interested. And the way that our day, we went for a couple of weeks, but the way that our days worked, we show up in the morning in Ted Newman's office, and we didn't know much. And he said, oh, yeah, that's good. Yeah, try this. Yeah, try this. And he said, come back this afternoon. And so we go off to Starbucks, and my colleague would be typing on a laptop, and we kind of come up with something else to take back to him and show him. And there was that sort of give and take and to and fro, which I thought was quite remarkable. Tom, yeah.
So you had said Eli Cartan was looking for classifying differential equations. And he came up with the same differential equation. So I'm wondering how he got, I mean, in classification differential equation, why did that differential equation come up?
Right. Wow, it's really hard to follow Cartan's work. But loosely speaking, yeah, let's bring the differential equation. Yeah, this top differential equation. If there's a 0 on the, yeah, it's.
I mean, is this the most general physical equation in some sense, or?
Yes, the most general equation of the theory. I just forget which category this corresponds to, because there's a way of categorizing differential equations with the right-hand side being things other than 0. Yeah, I just forget how it works now. Okay, yeah, shame he gave up on it, but.
When were the when were the second and third equations kind of found? Like you kind of talked about first one like that one, but,
Oh, yes, the others were found more or less at the same time.
okay,
Yeah, because I think Ted Newman and his people, he had a postdoc and a number of PhD students. They kind of realized there were two stages to the problem. They wanted a theory equivalent to general relativity. They wanted a theory which would produce space-time with the correct signatures, as I mentioned before, this word signature. So space-time you can set up as a matrix. It's called the metric, and the metric has signature minus plus plus plus, meaning that it has 3 positive eigenvalues and 1 negative eigenvalue. That's quite a stringent condition. And so the first 2 of these equations, they produce that matrix, but then the matrix has to satisfy the Einstein's equations in some setting, perfect fluid or whatever. And so then they came up with a third equation afterwards. Yeah. Yeah, go ahead.
Has there been any exploration of the null-surface formulation in modified gravity?
No.
Maybe there's a way of simplifying that equation just by the space-time you're considering, or the theory of gravity it reduces to.
Yeah, no, nothing has been done with modified gravity. No, not at all.
Interesting.
No, a little bit has been done. There's a guy named Gallo at the University of in Argentina. Yeah, I forget which one now. And he's looked at higher dimensions. So he's carried the null surface formulation over to higher dimensions, and it works just fine. Not a problem though.
Cosme or?
No, Casame's in Argentina too. No, this guy's Gallo. So I think he was perhaps his Casame's postdoctoral fellow, maybe.
Wow.
University of Cordoba. That's where it is. Mhm. Yeah, in fact, you know Gallo, don't you? Yeah.
any other questions? No, and then I think we'll just end it here. So next week we have Devin Beatty talking about the surveillance methods for wild pigs in cold climates. So that's next week's topic, but let's give one final hand for